Oh, all right. We are live. Welcome back, everyone. This show is called AJC and the Web Devs, Eric. So I always start off with welcome back to AJC and the Web Devs. So you are kind of a web dev. You got a website. You've devved the web for sure. But you are really more of a super AI specialist in terms of academic research. You are still working through your program, I think, right?
Mhm.
Yeah, so you're getting your PhD in something around AI at MIT with Max Tegmark, and people who know who that is know that's a really big deal. So why don't you start by introducing yourself and kind of how you got into all of this, and also for people who watch the show who've known me for a while, me and Eric have known each other for like 15 years now, like a really really long time, because we went to the same
Yeah,
summer camp together. And I first got to know you when you were just like a teenager. You were like 14 or 15 or so. How old were you when you started camp?
I think my first year of camp was in 2013. So I
Uh-huh.
was probably 14 at the time.
Okay. Yeah,
Yeah,
2013. So that would have been 12 years ago. And I know for a fact I was there. So I was there every single year.
yeah. It's been quite a while. Yeah, long time.
Yeah. Cool, man. Yeah, and it was so cool just like talking with you and hanging out with you and seeing that you were like, as just even in high school, you were obviously like super into math. You're like a math genius, is what most people considered you. So I was like, it's always, cool to see. I figured you would do something very cool once you actually got to college and studied it. And in certain ways, you kind of study what I would have liked to have studied if I had gotten into the stuff at a younger age and could have like had the foresight to actually learn to code in high school and get like an actual degree that would like be useful to me. So like seeing you go through this whole journey has been very, very cool. I haven't really been able to fully understand your research. So that's part of what I'm excited to have this conversation on, so I can get a better sense of what the hell you've even been doing, because I don't really have the background to fully understand it at first glance. You know what I mean. So anyway, that was a really long intro. So you can now speak for yourself.
Cool. Well, thanks so much for having me. Yeah, so I'm, as you say, a PhD student. I'm technically in the Department of Physics at MIT, but I do AI research. So my work tries to understand neural networks. And what does that mean? Lots of things. So we'd like to understand why certain properties of these systems are predictable. There seems to be this kind of order, these laws governing how systems change, for instance, as we scale them up. We want to understand what kind of structures they learn, how they learn them, and ultimately maybe be able to understand neural networks well enough in their internals that we could analyze them almost like we analyze some piece of code that someone has given us.
Like how you can deal with a compiler in certain high level ways, but we can't really do that with these types of models yet because they're super complicated and stochastic, right?
Yeah, I don't know if like the stochastic part is really relevant to this, but it's almost like this network that you get is like this fairly obfuscated, compiled program or something.
Because it goes through many
And
transformations and like iterations before you get kind of the thing at the end. Is that kind of it?
well, I just mean in hoping to actually like understand what the systems are doing internally.
Mm-hmm.
Like that might not be obvious from just like looking at like the parameters of the system as they sort of just exist on your hard drive.
Right.
And there's like a lot of work maybe that we need to do in translating kind of that description of the system into something which we can understand, like a computer program, like something that would be more interpretable to us.
Totally. And
Um,
this is sorry, go
yeah, well,
ahead.
maybe I should say just like a little bit more about like what how
Yeah,
I got
yeah.
here, because you asked like how I started studying these
Yeah,
things.
yeah.
So
Mm-hmm.
I was just a math major in undergrad, but I took a lot of things in physics and computer science. But I first started getting into neural networks because of this textbook from Michael Nielsen that I read in like the summer before my senior year of high school on neural networks and deep learning. It's a very, very good textbook. And Michael Nielsen was a physicist. He wrote like kind of the standard textbook on quantum information, quantum computation with this other guy, Ike Schwang, who also now happens to be like my academic advisor at MIT, separate from Max.
That's so legit.
Things
That's
kind of
incredible.
come full circle. Yeah.
I know. I remember when this book came out and I tried to read it. I got through actually a decent chunk of it. I think this is one of the few resources that actually kind of helped me understand what a neural network was, because something like Andrew Ang or Ng, and how was his name said? NG.
I think Ng.
Yeah. Andrew Ng, yeah, because he had his like Coursera course that was like machine learning, and that was kind of useful to me also because it helped me understand a little bit more of the math. But like the neural networks is always the complicated thing. So how'd you go, I guess, from like doing math and physics to like really honing in on neural networks? Was it just like this book really captured your interest?
Yeah, there's a couple things. There was this kind of just sense of curiosity and organic interest in it. I still remember like getting these things to work when I was in high school and like seeing the network improve over time. And the cool thing about, overtraining, and the cool thing about these neural networks, right, is that I mean, it's true that some of the math is maybe a little bit complicated, although not more complicated than the math that you would see in most like STEM subjects.
Yeah, but that's still itself fairly complicated for someone who didn't do STEM, which surprisingly many web devs I know were people who either studied computer science or just got into it like I did, kind of through a boot camp or just learning it kind of on their own. I think you'd be surprised how few like working developers who code actually got like a rigorous like statistical mathematical kind of background. I think it's less than most people would expect. Or I could be wrong, but at least that's my sample set of the types of developers that I've kind of got to know, which may be very self-selected, admittedly.
No, that's fair. But I think like the code for these programs.
We got Dev here. Dev's the kind of person I'm talking about. He got a CS degree. He got a college degree, found early useless. I think he got. What's up, Dev? Thanks for being here. You're gonna find this a very interesting conversation, I think. Dev studied computer science and he learned a lot. Actually, he's for his age and where he's coming in, he actually knows a lot more than I think he realizes. But I don't think he took a lot of classes that were math related. He may disagree, but that's my perception, at least having never asked him about it. Just
Yeah. But I guess like the point I was just making here was that like ultimately the length of these programs that like define like the basic kind of logic of a neural network and the training. I mean, I think like Michael Nielsen's implementation in that textbook, like if you remove the comments, it's like 70 lines of Python or something. And so there's this kind of simplicity to the programs themselves and like to the basic learning algorithm. But then there's this kind of complexity that is learned when the systems like interact with data and when they train. And it's just very cool to see that and to see systems learn. So that was kind of what was exciting about it at the beginning. And then eventually in college, I was just thinking about what kinds of problems seem really open. Like there's this advice that maybe you should seek out fields where things seem messy. And like, that's where there's opportunity to try to make progress on theories that
like somewhere there's not a set paradigm yet in the Thomas Kuhn sense.
Yeah. And that's also very difficult. Like maybe in ways I didn't anticipate.
You have to be naturally curious and actually be interested in it and not just kind of going into the thing where it's like, I just need to get a degree so I can get a job, so I can do this, so I can do that. It's not as goal oriented. It's more like I need to immerse myself in this set of topics and subjects to reach the frontier to then make a meaningful contribution to it.
Yeah, I think probably, I mean, most scientists are like pretty immersed in their subject. But there's a kind of like order that maybe some subjects have where it's like, it's pretty clear like what a chemistry paper looks like, what it means to have like a good result in chemistry. Like it's very organized kind of that science and you're not really maybe like thinking about reconsidering.
This is why AI
the
people love
basics of the
benchmarks.
field.
They're obsessed with benchmarks. They're trying to attain that type of order through the benchmark, but the benchmark is inherently limited in terms of what they're actually doing and built, in my opinion.
Yeah. Yeah, there is something there. I mean, like even like what it means for an AI system to like have some capability is like I don't know, maybe just like you define a benchmark for the thing that you care about, you do your best, and like if the system does well on it, then it just has that capability in some meaningful sense. It's a little unclear though, like you know, often if a system does well on some task, like how it's doing well, what that means about the internals of the system and the cognition that it's doing. But anyway, I felt like it would there's interesting stuff to be figured out about understanding how neural networks work, and so I just wanted to do that.
Totally. So just to help with the timeline here, so what year did you start your like actual research into this in terms of your PhD program?
2021.
2021. Okay, yeah. So been doing it about 4 years now. That was a good time to get into it then, because that was pre-ChatGPT. Like GPT itself was around, GPT-2 or maybe even GPT-3 by that point. But you were still kind of ahead of that AI curve in the sense that a lot of people probably jumped into these PhD programs in 2023 and 2024, if I had to guess.
Yeah, although I don't know, like it feels like even at the time, like in 2020 when I was applying to these places, it felt late because deep learning had, you know, people have been working on it for 8 years, you know, or more. It was already very competitive. Like the AI PhDs were very, very competitive.
Yeah, it hadn't punctured that bubble though, out of academia into the real world, where it's like my dad and my wife both use ChatGPT like frequently. That's very different from where it was at, where there was these like theoretical things or like kind of toy things or stuff that could do really impressive things like AlphaGo, but like that's not something you can like the average person interacts with or does anything or solves any of their problems. It's like beating the best Go player in the world is neat, but what does it mean to me? It's not the same, you know?
Yeah. It was good timing in that way. Like it's surreal to have like the whole world be talking about this subject, because yeah, back in like 2020 there's sort of the early scaling laws work. You know, OpenAI scaled up to GPT-3, and there was a lot of kind of hype within this like fairly narrow, weird community around like what this means for the future. And now you like look, and every interview at Davos is just about this topic. Like it's about scaling laws. It's about you know, language models, and it's just weird. And you know, also to have like your friends and family be your AI consultant. You know, I think like everyone I knew, you know, all their family was asking them about DeepSeek like a couple months ago, what it means. So
yeah, no, my doctor asked me about DeepSeek. That's super funny. Yeah, and even though you started studying it formally and officially, I remember you and I were talking about this back when I was first getting into it, and that was around like 2016, 2017. So you've been aware of neural networks themselves and deep learning, and that's where I want to start us off in terms of like defining terms and things. Is the first thing you had said is basically you're like getting a PhD, you're studying, you're working with neural nets. That was like the high level term you use, and that's useful for me as someone who's followed this subject for a long time, because I know what makes a neural net different from a classical kind of algorithm. Where I don't know so much now is what is it still a neural network that's powering things like ChatGPT and language models, and how does that interplay with things like attention and the reinforcement learning done to them afterwards, and like how much is it still relevant to just like have a neural network that you know how to do things with when the things you're actually interacting with are going through all these other steps and have these like additional kind of add-on parts. So those are some of the general things I'm curious about. So let's just start with like, how do you define a neural network itself?
Yeah. I guess I would say like, you know, a neural network is a system which is sort of loosely based off of the structure of the brain very loosely.
It has neurons that click on and off, and there needs to be a certain gate reached for it to be on or off, essentially. So it's not a binary thing, but it's kind of a binary thing.
Yeah, I guess you could maybe say like most artificial neural networks have artificial neurons.
Right.
So they consist of a large number of units, which individually perform this little computation where they take in some set of inputs and then either sort of fire or not fire. Although in practice with artificial neural networks, they fire or they don't fire or they fire in some continuous way. But they're systems which consist of a large number of these basic units, which take in a bunch of information and then output a piece of information. And then you sort of take a large number of these units and you sort of stack them. So the input to the network is some data, and then you have some set of units which individually take in a bunch of information about the input and then perform this little computation, give a little bit of output. And then you have another set of units whose inputs are no longer now maybe just the input to the whole network, but are the output of another set of neurons. So when people talk about deep networks, there's this thing where there are sort of these layers of neurons, of units, where their input is the output of other neurons. And so people sort of build up these computations through these layers of individually simple units. And the key is that these things have a lot of flexibility in terms of the kind of functions that they can implement. And we can also train them so they're good at learning to approximate different functions. And I'm realizing even now, like function and approximation maybe are terms that like I don't know, like if they're
you probably don't know what signals is because you're not super into front-end web development, but Dev saying it's almost like signals, which I have no idea what he means by that, but he's very deep into signals, so it's kind of like everything can be everything when you start to map different concepts onto each other. But the training part, I think, is what helps click a lot of this together. Because when you describe the thing, signals is basically Excel spreadsheet cells. So that's interesting because when you talk about the neurons, is that kind of what like the parameters are when people talk about a model having 7 billion parameters or 14 billion parameters? Is that a similar thing? Are those related?
Yeah, generally they're related, but they're not identical. So one neuron will typically have lots of parameters, but it's maybe something like on the order of
the number of neurons is related to the number of parameters in some sense, even if it's not one-to-one.
Yeah.
Gotcha.
Now, you also mentioned things like attention. There are lots of things that people do in these neural networks that don't just look like the description that I gave of just like a large number of units performing this computation independently of each other, passing that on to the next layer. There's other more complicated operations that people have figured out how to do, where I don't know if it makes sense to explain attention right now. I don't know if it's actually even all that relevant to the discussion we're going to have, but basically there's not a particularly good like definition I feel of like a network, because there are a bunch of things that people include in networks that are not necessarily closely analogous with what's happening in the brain. And although that's kind of a tricky question, but
yeah, the brain thing is an interesting historical connection in terms of like how these things are first created, and they go back to 1945 with McCullough and Platt. What was the other guy's name? Pitts. Yeah, and sounds like an old kind of concept. But I'm more curious about like the things we're actually interacting with today. How similar is that to just a classic network? Is it a classic network with a bunch of other stuff on top? Or does it kind of stop making sense to even think of that as kind of like the base of what's happening with a large language model?
It's so the like original perceptron work from like the 40s, 50s, 60s, this kind of thing. I forget exactly how those networks were set up. But
they would create the parameters manually, I think. Because I remember Frank Rosenblatt had like dials he would tune, I'm pretty sure I read something about that. He had an actual machine with dials he would turn to create the neural network.
Yeah, I think that at the time that people were not, I mean, certainly not training networks with like backpropagation and gradient descent, which is what like people do now. And then I think there were also limits to the types of functions that the early networks could express. So there was this whole paper from like Marvin Minsky criticizing, it's called perceptrons, like criticizing perceptrons.
That's to create the first AI winter.
Yeah.
They say.
So yeah, there were certain sort of functions which, or certain operations, certain things that you might want networks to do, which like some of these early things couldn't express. But this ended up not ultimately being a limit because there are ways of just making the networks more expressive, and then now we also know how to train them. One fun thing, by the way, about Frank Rosenblatt is that he eventually got into like looking for aliens. So he was doing SETI stuff. And yeah, this is a crazy connection. I had no idea about this because like we just think about him as, you know, doing neuroscience AI stuff. But there was this like SETI conference in like the early 70s. It was like organized by Carl Sagan with like all these like scientists, like, you know, even like Marvin Minsky and you know, biologists were there, and it was a really interesting conference. And Carl mentioned this paper from Rosenblatt. I was like, oh, that's interesting. Because he said, you know, my colleague at Cornell, Rosenblatt, whatever. And it was on basically a way of like identifying when planets transit in front of stars. So it's like a way of trying to find exoplanets. And yeah,
you did SETI, didn't you? You actually worked at SETI, right?
I did, yeah.
That's super cool.
Anyway, there's some story about like how he died young, but there's some story about how when he was sort of up for tenure, like someone advised him, like, you know, put off the SETI stuff for a little bit, and he was just like, yeah, whatever. I'm gonna keep doing it. Like, just kind of disregard for yeah, like
good for him.
His career, I guess. But yeah.
Okay, so where I wanted to go from here, unless you had something else you were gonna explain, is that kind of first we defined neural nets, and then I want to talk about kind of the training, like how are they trained, what are they trained on? This is something that I think is really important, especially now with how large language models are created, and it's sort of glossed over by a lot of people, and it's also very hard to even get a sense of because many of these models are trained on data that we don't know about or that we're not given access to, and there's no real disclosure around the data that's being used to train these things for lots of reasons, legal and non-legal, and shady and non-shady.
Yeah. Right. I guess I don't know what the Frontier Labs train on. Presumably,
no, that's what I'm saying.
Yeah.
Only the people who work there know.
Yeah, but for systems like language models, the core thing that these systems are trained to do is to predict the next, basically, word in a bunch of text documents. So you basically scrape the internet, you find as many documents of sort of human written text as you can, and then you train these systems to predict what comes next, given what came before it in the document. And it turns out that if you do this at a large enough scale, this training objective incentivizes the network to learn a very large number of things about the world. Because in order to predict the next word well, you need to know lots of things. So if, like, I say, you know, like the company Anthropic is located blank. You might say in San Francisco or something. And so in order to predict the next word there about something factual, you need to know the fact that relates to it. But it's not just facts, it's also things like different skills. So for instance, on the internet, there are like a large number of lists where some text is organized in these, whatever bullet point lists, or there's something that's incrementing, increasing.
Like the 100 sweetest guitar solos.
Yeah. And it'll count 1, 2, 3. And if you're going to be able to predict in certain places in that document what word comes next,
how would it know that Stairway to Heaven is supposed to be number 1?
Yeah, well, just in terms of predicting the numbers, like the system needs to be able to count. So basically, implicit in this objective of predicting the next word are a whole bunch of other skills that you need to learn and that networks do learn. And in learning how to predict well, they can also then generate new things.
Okay.
That doesn't really tell you very much about like how the networks are doing that internally. And also we haven't really gotten into the math of how the training works. Okay. I mean, maybe just a couple of things we could say there, or that like...
I would say in general, try and explain the things you think will need to be understood for your research in particular to make sense, because that's where I want to get us to.
Okay. Maybe we don't need to say that much other than that the things that are updated in the network during training are just a large number of these parameters, which govern like the strength of the connections between neurons, basically. And everything in the network, when you just look at it, is just a bunch of numbers. So the actual sort of input into the network, when you show it a bunch of text, are basically these lists of numbers, which each represent a word. And then these lists of numbers sort of become transformed in the internals of the network into other lists of numbers that are not necessarily scrutable. They're just a list of numbers. And then eventually, when the network makes a prediction, that's also just an output, which is a list of numbers. But in particular, it's a list of numbers which are probabilities over what the next word is.
Okay, this is great. I just want to hook this into a couple terms that I know people know who actually work with this stuff, is tokens and embeddings. What do those terms have to do with what you just said?
Okay, so when I talk about words, I mean tokens.
Great.
So it's predicting the next token. Yeah. And the embeddings are, so within a transformer, there are like learned embeddings. These are like the first layer, basically, of the network. Is just like it learns a list of numbers for every token. These are then input into the network. And then this gets transformed into a different set of vectors.
Sometimes that's what I thought this stuff mapped together. So that means I understand what you were saying and actually knew what the hell was going on, which is great. So I'm like, I think he's talking about tokens and embeddings right now.
yeah, exactly. And although when people have like an embedding model, I think that I haven't really worked with like.
So when you create embeddings, models, it's not like a model. You basically you use one of the embeddings like endpoints for OpenAI, and you feed it some like text or something, and then it gives you back literally like a JSON file with just a array full of numbers. It's exactly like it's a list of numbers, literally.
I think probably what's going on behind the hood there is that they run that text that you gave it through a network, or at least through several layers of a network. And so that embedding that you get back are like the firing patterns of the neurons at a particular layer of the network.
Fascinating. Yeah. Wow. You just blew my mind. Because I learned a lot of the stuff you're talking about I learned at a conceptual level a long time ago, and it was like, okay, I get what people mean when they use these terms, like the overall goal and what's happening, what the network is, and how it's being trained and how it's being transformed, and what like the whole point is. But as like ChatGPT started to come out, I was working with that, and I'm like, I have no idea how this connects to all that other stuff I learned back in the day. And then you just kind of learn the terms it uses to mess with it because you're a developer, and you just start using the API, and you're like, okay, so I'm allowed it costs me a certain amount of money for tokens. So what's a token? You find out what a token is, and then you understand that it inputs a certain amount of tokens, outputs a certain amount of tokens. And then there's like this thing called embeddings, but like there's not been a clear connection for me to what is actually going on under the hood, because they don't tell you a lot about that, and it seems very disconnected from all this other academic research that's happening.
Yeah. Right. Well, I don't know like how accurate all of the marketing terms are, but yeah, like the tokens are the tokens like that are fed into the model, and the embeddings are like internal activations in some network.
Awesome.
Slightly confusing because like we also talk about the embeddings as being just this thing that is learned in the first layer of a transformer, just sort of like the raw like token embeddings.
Right.
So there's sort of a difference between like the token embeddings maybe of a particular language model and the like embeddings that you get from like the OpenAI API. But
right, yeah, interesting. There's one other thing I wanted to ask based on what you've been saying before, and then we can kind of start going through your slides and stuff. When you're talking about how you train on different things, we can gain like kind of world knowledge and stuff. There's something that I've heard. I've never really know if it's true or not. It's something like people say that the models got a lot smarter once they started training it on lots and lots of code, because code is highly structured, complex, and works in a very specific way. Like you have a long program, like if you change one thing in that program, the entire thing can break in very weird, unexpected ways. And so I heard that they said like when you trained on a crap load of open source code, it would then get better at, other just like answering, just being smarter. It became a smarter model in general. Is that actually true? Have you heard that? Can you verify that?
I've heard that. I don't know quantitatively how strong that effect is.
Mm-hmm.
It seems like I would expect there to be some effect where training on certain types of things helps with seemingly unrelated things, but there's going to be a limit to that. So like, training on a bunch of code doesn't necessarily help you answer like factual questions about history or something, but probably there are some benefits where certain very like generally applicable skills are learned from this like very broad distribution of things. And like maybe in order to learn certain skills, like you need to train on code, maybe you also need to learn other things, train on other things. There's this kind of tricky connection between like, it's a little unclear in general what that objective of training to predict the next token actually incentivizes the model to learn.
Right,
so
that's
for
where you get to
instance,
reward and stuff like that.
yeah, but even more basically, like you could imagine, you train on a bunch of code and it's like, well, what has it learned? Like maybe it's learned like a bunch of like lower level knowledge about the names of different libraries and modules within different
Well, it should learn
companies,
like
programming languages.
logic and like if then else then and stuff like that.
Yeah. Right. Like a strong enough model at predicting code would like basically be able to sort of simulate a lot of how maybe that code is executed and things like that. But yeah, like really understanding it and being able to think logically about it probably would be incentivized eventually. Yeah.
Yeah, I think there's an interesting thing where not just in the training, but when you're actually using them, something that you used to have to do, it's less of a problem now, is that the first kind of iterations of things like ChatGPT, like couldn't do math, like it just sucked at math for some reason. But if you told it to write a program to do the math, it would write code, and then the math would be correct because it would know how to write the code to make sure the correct answer was outputted. But if it just answered just in its like text, it would mess up math. It doesn't really do that anymore, as far as I can tell, but it did that a lot in the beginning. It just couldn't do math.
Yeah. Well, it's kind of a hard thing to do, just because of how the networks are set up. But if you're predicting if you just write out like a very long multiplication problem, like of 10-digit multiplication or something, and then you ask the model to give its answer straight away, then within what's called like a single forward pass, it has to basically compute the full multiplication, because the first digit of the answer is like kind of the hardest one. Like if you were going to write out that multiplication, you would actually
to solve the whole thing to know
the leftmost digit at the end,
answer,
and then so there's even the weird ordering stuff like that. This is also partially why like chain of thought is so useful, because it means that like for problems like this, the model doesn't have to just like come up with the answer in the limited amount of steps that it has internally during a single forward pass, but it can like spread that computation out across lots of forward passes.
Totally. And chain of thought, for people who don't know a specific term, is when you use a model like R1 or to a certain extent O1. There's a controversy here that I want to get into also. It will first kind of think out its answer before it actually gives you the answer, and you can kind of click it and open it to see it or not. But I've also heard that ChatGPT doesn't give you the reasoning tokens. So I think what people mean by that is that the actual reasoning tokens are being summarized before they're being given to you, whereas R1 gives you the first original ones unsummarized. I don't know if that's actually correct or not, but that's what I've been trying to understand about this term and topic and what's going on.
Yeah, I think that's right.
Okay.
Yeah, OpenAI does not reveal like the exact output of the model during chain of thought.
So what is it showing you then? And how does it get that? Is it just summarizing it, or is it just like rewriting it to make you think it's thinking a thing that it's not? Like, what are you being shown that if not the original chain of thought? 'Cause you do see something when you use O1.
Yeah. I think that they have a smaller language model that is summarizing the chain of thought. Yeah.
Okay, so I got it right then. Is my current perception of what is happening is correct. Okay. Yeah, that's a really, really strong reason to use R1 then, honestly, because it really helps. And I felt that when I used R1 the couple times I've used it, I'm like, this is a really long, detailed chain of thought. And I think it might be the same for Grok. I once did a Grok thing. The chain of thought was like 10 times longer than the actual answer it gave. I was like, what the heck? This is a ton of thinking it's doing.
Yeah, it's cool to actually see that. I mean, I think if you give O1 a really hard question and it thinks for a while, it is outputting thousands of tokens or something. It's just you can't see it.
I mean, you're paying for it, aren't you? If you're using the API, you are. Like, you pay by the token.
Yeah, you're paying for it.
Very, very weird.
I
can see why people complain about that.
API pricing works, but I think the reason they did that is because, I mean, as we sort of see, for instance, with DeepSeek, you can distill much smaller models, given a bunch of examples of that reasoning trace, and basically get the smaller models to be pretty good reasoners. And so, like OpenAI does all of this like very expensive, although not super expensive yet, reinforcement learning to get the models to figure out how to reason, and then it's relatively easy to potentially create other models from that without doing a similarly expensive step. So it makes sense why they would do it.
O3 mini and O3 mini high, and then we're eventually going to have actual O3. Is that kind of like why we have all these weird different model names, because they're distilling them into smaller versions?
Presumably. I don't know how like O3 was trained, but yes, I think the speculate. Well, it's interesting. So it could be a distillation of like the full O3, or they could have just done like reinforcement learning directly on a smaller model.
Interesting.
Yeah.
Don't forget O2, the only option. So the two people in the chat right now are two of my good like web dev friends who are doing plenty of stuff with AI, but don't have all this like academic background as far as I know. But we should get into your website. You have an interactive website, which I think will definitely help a lot. So you want to share your screen and kind of mess around with that and try and understand what your thing is.
Yeah,
How'd
sure.
you build the website, by the way? Did you code it yourself? Did you have like an LLM help you with it, or is it fairly easy to just embed this kind of stuff into your website?
This is like the like interactive thing where you can look at the curves. Yeah. So I'll share my screen. Okay, so yeah, I made this website to illustrate some facts about how the networks learn and how they scale. But it also, I think, is just a nice way of thinking about, or just like directly looking at how, at the task that the models are trained to do. So what I did was I took a small model. It was a like 400 million parameter language model.
So where did that model come from? Did it have a name, or like is it?
Yeah, it's called Pythia 410 million, and this is part of a sort of family of models called the Pythia models, which were released by Eleuther AI.
Okay.
But the nice thing that Eleuther did was they released like a large number of intermediate models. So they released the final model after training, but also a bunch of other models. So you can see how these language models change during their training process.
Yeah, this is cool. I don't think I knew about this company, but I like what they're doing. It says empowering open source artificial intelligence research. And I think that was really great. I think that is sorely needed for this stuff.
Yeah, they're really cool. There's some really great people at Eleuther. But what we can do is, because we have all these model, they're called checkpoints, so stages of the model at all these different points in training, we can see how the model has changed throughout training. So this is not going to look necessarily at the internals of the model, but we are going to see how kind of the behavior of the model.
So we're looking at the outputs of the model, basically.
But
the internals.
In particular, though, we're going to look at the error of the model. So what I show here is each of these gray points represents a particular token in the corpus.
Can you use your font 2 times?
Like that?
That's probably good. Yeah. That's perfect.
Okay. So we can basically click on each of these points, and what I show when I click on each one of them is a token, and it's highlighted in red down here. It might be kind of small to see. We see that token in its context. And so the thing that the language models are, right, so this is just a whole bunch of text on the internet. Probably there are some things in here which are going to be fairly disturbing if we like searched around for long enough.
It said context not loaded. So is that it moderated, or why does that say not loaded for security reasons?
Yeah, basically
has code in it.
Yeah, I chose not to display any code because I was worried that like
maybe it's like JavaScript SQL injection type stuff happening.
Like the code would be run.
Sure, yeah.
I don't know if that was
itself should sandbox anything too crazy, but I guess that makes sense if you have like you could grab your cookies or something like that, I guess.
Yeah, I didn't think too much about it. Maybe it was unnecessary, but
it's better safe than sorry, probably.
Yeah,
especially for what you're trying to show here, you know.
Yeah, because there's still other code we can look at in here, but basically, what we show is the model's error in predicting each of these tokens. So it's called the model's cross entropy loss on the y-axis of this right plot. And this is just measuring how sort of correct and confident the model is in predicting this token from its context. So we can see, for instance, there's this little cluster of points out here. And these actually correspond to predicting S after an apostrophe token. So this is actually a pretty easy thing to predict because S's come after apostrophes in these examples, at least. And we see that the model eventually, pretty early in training actually, gets basically zero loss or error in predicting this token. So very early, and by the way, this curve shows the model's loss over time in training. And so we see that like fairly early in training, this scale is on a log scale. So it's going from 1 to 10 steps to 100 to 1,000, 10,000, and 100,000 steps of training. This is like the amount of time that the model has been training. And we see that pretty early on, the loss drops, and then it stays very low. So this knowledge that S's come after apostrophes is learned very early in the model's training.
And this is super duper important, I think. Tell me if I'm right about this. This research is super, super important because a huge amount of money is being spent training these massive ass models. And if you can figure out exactly when you need to stop training it for it to do what it needs to do, you'll save money, essentially.
Yeah, that's not like I don't know if we're there yet in terms of
but
like
ideally
being
if you
able
learn
to
this
predict.
Yeah, but that's the point, though, to understand it well enough to be able to do something like that. Even if not perfectly, but better than just guesswork and just running it and then kind of checking it every now and then. Like, is it do the thing yet? I don't know. Keep running it, you know?
Yeah, the overall motivation of this kind of just basic exploratory stuff is to try to build up the like general theory of how training networks on more data and training larger networks changes them.
Changes you're trying to understand the scaling laws to a certain extent. Maybe not only that, but that's a big part of it, I would imagine.
Oh yeah.
It's tight. That's tight.
Yeah.
So I think this is really important. There's so much money is being put into training these models, man. I'm telling you, it's an amount of capital we've never even seen before.
Yeah, so it's quite striking that like given the economic importance, the like geopolitical importance of what is going to happen when people continue to train larger systems, it's crazy.
Probably a surprisingly few amount of people studying it, I would guess.
Yeah. Now maybe internally at these labs.
That's part of the problem, though, is all this like weird hidden internal knowledge at these companies. And I understand it, you know, I get why companies have secrets, but at the same time, it puts a test to their rhetoric about what their actual purpose is.
Yeah. So there's not as much like very ambitious, like trying to come up with these like unifying theories, I think work that's open. There are various models of neural scaling. Our work is one of them.
And I have to imagine that's the stuff that wouldn't be being done internally, these companies, because they wouldn't really care enough. Like they want to learn how do they actually do this practically in a way that makes sense for their systems in the cheapest, fastest way possible. And that doesn't necessarily involve coming up with a unifying scientific theory.
You'd think, though, that it would have applications if you did in fact understand what is going on in these systems really well. You'd think that it would have applications for making them more efficient, or implications for what to do differently. Maybe, you know, ways of changing the objective that the networks are trained on or something. But I don't know. Yeah.
Well, I guess, do you know how much communication there is between people actually at these companies and people in academia, like where you are?
There's very little on the kind of on this sort of topic related to like scaling laws and that sort of thing. I mean, there was a few years ago. There's a paper from some folks at Google and also then at the time OpenAI. Jared Kaplan, he was a professor at Johns Hopkins, and then he was at OpenAI. They actually released their original paper on scaling laws, like documenting scaling laws for large language models. That kind of thing maybe would not. It's called Scaling Laws for Large Language Models.
It's a good name for a paper.
Or Scaling Laws for Neural Language Models.
Gotcha. Yeah. Dev said in the chat, Manhattan Project V2. Is that what needs to be done to move the needle?
Progress is going pretty quickly right now, just with a bunch of separate private companies. I'm not sure that things would happen faster if there was some messy reorganization and like everyone was meant to work together. I mean, keep in mind that like these people don't necessarily like each other that much. I mean, a bunch of like all the founders of Anthropic, they left OpenAI. Now a whole bunch of people at this new Thinking Machines company, they're also have just left OpenAI. So I don't know, maybe
that's true. That's what a lot of people I feel like who aren't super into the minutia of these companies don't realize that is that Anthropic is an offshoot of OpenAI, right? Like how many people do you think were actually working there that ended up hopping ship and then joining Anthropic or creating Anthropic?
I mean, there was like an original group of like 7 founders.
And were they also from Google?
They were mostly from OpenAI, if not entirely from OpenAI.
Okay. Or like they worked at Google before they had worked there. I don't know. I feel
some of them. Yeah. So for instance, Chris Olah, who's one of the main people doing interpretability of neural networks, he was at Google Brain for a while before OpenAI, and then now Anthropic. Yeah. I think he was at Google Brain. Yeah.
Okay, we had kind of tangented from what you're talking about in terms of your project. So continue on that.
Oh, yeah. Okay. So basically, the high level point here is that I want to like try to directly visualize like a large number of different like skills that the model has learned that it turns out are incentivized by this prediction, this sort of next token prediction problem. Mm-hmm. We see that the model has to predict a bunch of tokens. Some tokens are predicting an S after apostrophe, so it learns that this is what it should do when it sees an apostrophe. There's another set of tokens, which are actually down here in this sort of group on the bottom right. These are actually all involved predicting a new line after another new line. So this is also a very common pattern in text, is to predict a double new line in order to create a new paragraph. This is also learned extremely early in training, and the model is able to be very confident and correct in its prediction. Now there's a whole bunch of examples like this, which are super interesting. So up along the top part of this group of points are...
I just saw code, actually. One of the ones you just clicked.
Oh, yeah.
It had some CSS in it, I think is what it was.
Yeah, I'm trying to find a good example of what I'm referring to here. If I go more...
It's an open source license. This is fascinating. All this stuff, like, because you'll just by seeing the chunk, a lot of times you can tell what it is. You can see it's a part of a legal document, or it's part of like there's some code right there as part of a license.
Oh yeah,
like that, or
there are a lot
sources like at the end of a paper or stuff like that.
Yeah, there are a lot of licenses, code licenses, on the internet because so many documents contain these licenses at the top of them.
Because they're public, models, they're all almost every GitHub repo, or most of them have a license.
Yeah, so it's learned like very early, and it's learned by models that are relatively small. Like they'll know the licenses. But if we look at a token like this, what's going on? So here it's predicting when, and we see from this loss curve that the model pretty quickly gets very good at predicting this token because its error is super low eventually.
Yeah, because there's a clear pattern. This has to look at the last couple and see that they all ended when.
Yeah, so there's this pattern of like the remainder when, and this is seen throughout the context. And so I think the idea is that within the context, the model is making this inference. It's like doing induction. It's like, oh man, when has occurred here after remainder a lot. And so now remainder is the previous token. We're going to predict when. This is interesting because it's different, I think, from the model learning that this is a common pattern in training. Like some of the other examples where it's like it's maybe predicting a new line after a new line, that might just be something which it's learned from training. But here it's almost like within the forward pass, when it's predicting when, it is doing a kind of learning, and it's looking at the text that it's seeing right now and making an inference about how it will continue based on the statistics of the text as they occur in its context.
Right. Yeah, that's what I was going to say. So it's doing something with the actual context itself that is relevant, the in context stuff.
Right. It's like this is not necessarily encoded directly as like this crystallized knowledge in the model that like when always follows remainder. But it's like a kind of learning maybe that is happening on the fly when we're evaluating the model.
Yeah, this is something that is actually super relevant to me and how I work with these things. And so something I've thought about and worked with a lot is that when you're trying to get it to understand like your code base, how many files do you need to give it to answer the question you have or build the feature you want to build? And usually what I'll do is, and by structuring my code base itself in a way that I can do this, if I have a feature I want to build, it's usually I have to touch a couple code files. So I'll grab all those and then like one or two that give it context for like the whole project, and I'll just dump it into the chat and then tell it what I want the feature to do. And I have some presets also in terms of how I want to write the code and how I want to respond. Yeah. And then it will give me an answer, and then I'll kind of like try and implement that and see if it broke. And sometimes I'll realize, oh, there's this other file here I actually should have given it. And sometimes it just works right away because I got pretty good at it. So all of that is just based on it being able to use the context of the very first input it gets to answer something that it wouldn't have been able to do if it didn't have that context.
Yeah, and there's even a name for this like learning that happens in context. It's called in context
learning. Yeah, this is what I've been using that term and telling people that's what it's called. So I'm glad to get your verification. I'm using that term in a strict, correct sense. That's what I've been saying to people. I'm like, you have to figure out in context learning. It's like a super, super important part of this.
Yeah. And you can be more and less precise about like how specifically you use that term. I mean, some people have worked out that like the kind of learning that happens in context learning is like almost like the training of a model like within the computation of the network or something.
Because it could take in a ton of text. Because originally these models couldn't take in a lot. Like when I was using ChatGPT like 3.5, it could take very little, like
2,000,
and
4,000
now like tokens, you can give them tens of thousands of tokens, a ton.
This is it's probably like I don't understand the results well enough to be able to really talk about them, but there's crazy stuff that people have worked out about how these models, these neural networks, just in the process of the computation that they do internally, all of these neurons firing, can effectively like almost like spin up and then train like a smaller model within them. And so there's these papers on how like in context learning is approximating something like gradient descent and the sort of thing, which is crazy. But I don't know exactly how it works in general and in real language models. For something as simple as this, where it's basically just copying from the context, we kind of do understand how it does that. And there's this whole other paper by Anthropic called In Context Learning and Induction Heads, and also this other one which it's building off of, called a mathematical model of transformer circuits, which sort of describes how this happens. But it's interesting.
Both those and putting them in the description for YouTube.
Yeah, it was super cool, especially in context learning and induction heads, because like we can observe this behavior of like, okay, well, the model is good at doing this copying, and we can see that it seems to be learned early in training. And people then also go into the model and they try to understand what particular sort of like mechanisms, what particular neurons sort of implement this behavior or implement this algorithm, which allows the network to sort of copy text that it's seen earlier and then like paste it into what the next answer, what the next token will be. And we might hope, and this is sort of what motivates a lot of my work, is we could eventually sort of identify like a huge number of different mechanisms in the model that each implement some particular behavior or encode some particular knowledge, and then try to decompose this whole complicated network into much simpler parts that we could understand.
Right, because right now, when you're just clicking random places showing you different text, like I was saying, there's some that's like legal documents, some that are licenses, some that are like creative writing, and so those are all fairly different things we want these models to do. Like when you're using it, if you're trying to analyze court documents, that's very different from if you want to write CSS. That's very different from if you wanted to write a poem, you know?
Yeah, exactly. So, like, I don't know, this also relates to questions about like what intelligence is, because we tend to think about, I don't know, intelligence as just this like general problem solving ability. But it seems like the things that the models are incentivized to do, like language models, is they're incentivized to like learn a very, very large number of crystallized skills and knowledge. And this is it's interesting because, you know, maybe we could hope then to enumerate what these pieces of knowledge are, what these skills are, and decompose the network in that way.
Yeah, I think the difference between intelligence and knowledge is like super important here. So when we think about intelligence, and especially like IQ, like some of the tests that they give are things where it's like, you know, the 9 boxes, you have to figure out what the 9th box is based on this pattern that goes throughout all of them. And it makes sense. Like, but that's like, I think of that as like, you know, raw computation. Whereas like that's not the same as like knowing, you know, all the different species of animal or something. Like there's a bunch of the facts and then like how that stuff all fits together. And that's what makes the models really interesting, is because humans, we have a certain intelligence, but there's also a limitation, just how much stuff we can shove into a single person's brain. And a model doesn't have that limitation. That's why you could ask it 100. This is what Tyler Cowen talked about this one, so I thought it was really interesting. Someone was saying, what would happen if you pit, Tyler Cowen, the economist, versus an LLM, just asking on economic questions. And he's saying that he would be able to do good for a while. And when you ask him questions like about his discipline and about his specific studies in that discipline, he'll be able to get better answers. But as you ask more and more questions, eventually you'll just ask him things that he doesn't know, because he can't know everything, but the LLM will know. So he was saying it's not a question of like who's smarter, but like how many questions are you asking? Because at a certain point, you're going to reach the limits of his knowledge, and the LLM goes far beyond that.
Yeah, it is astonishing the depth of the knowledge that is crammed into these systems, especially given that they're not huge. I mean, they're big, but there's an immense...
They're too big to fit on my computer. I can't fit the largest llama models on my machine, so they're pretty big. I would say that's pretty big.
So we have like 70 billion or like 400 billion parameters or something, 600 billion for DeepSeek, but the total amount of information stored on the internet is much higher.
But it's redundant though. So much of it is just redundant, or it's just meaningless. Just people talking about their cats and stuff.
Yeah, but anyway, I guess if we compare this to number of connections like in a human brain, I think that the parameter counts of the networks that we have today are not necessarily bigger than the number of connections, the number of synapses in the human brain. So it seems like these models are much more knowledgeable than any human, but they're also smaller, maybe relative to the amount of information that can be contained in, or at least the number of connections in a human brain. Yeah, so they might be more efficient.
And that probably has the big implications for, the whole Kurzweil scaling law that had to do with because what he was doing when he was looking at how to get to the singularity, he was looking at things like number of neurons and how long it would take to compute the same amount as a human brain, and then beyond that. So if we actually need less than that, because everyone expected it to be more, probably because they're like, they're going to be harder to train. They're not going to have the ability to reach out into the real world. So they would need to have more connections than humans. But you're actually saying it's the opposite.
Yeah, at least as far as I can remember, in terms of statistics here, I want to say it's 10 trillion or 100 trillion connections or something in the human brain. We can also ask how much compute it would take to simulate a human brain throughout the course of its life. And so this is also something people do when they try to estimate how long it'll be until we have systems that are at human level.
Because they want to upload their brain into the noosphere. That's what they care about. So that's very relevant to
them. Yeah. Well, yeah. Although also people use arguments like this just to try to estimate when we'll achieve AGI. Sure, yeah. Where it's
which makes no damn sense. I would just pick random numbers to be once we hit this number, we'll have AGI. It's but why?
Yeah, well, or even there are these. I saw some. Maybe it wasn't even actually from Anthropic, but I saw an image with Anthropic design, and it was whatever, we have roughly human level coders within a year, and then in 2 years, 3 years, it's we have systems that are coming up with novel scientific insights and accelerating science massively. And it's interesting because it's well, on one level, maybe it is kind of intuitive that there's this progression where once we have systems that are at parity at a bunch of tasks, then if we continue to scale them, with humans, then as we continue to scale them, we'll reach this point where they'll have novel ideas. But there's not a guarantee that that's going to happen, and it's possible that there's just a kind of different shape to the skill sets of these systems and of humans, and it's not guaranteed that we're just going to get certain capabilities magically, I think, at certain scale.
I don't know. I have a pretty contrarian take on this, which is that I think we hit AGI a year ago, and that right now everyone's moving the goalposts and picking new definitions for it, because by almost any definition we've hit it. The novel scientific idea stuff, there's been papers, I saw at least one, maybe it's, spurious, but they had a model come up with a bunch of new ideas to research and then put them up against people and then had scientists judge between the two, and they said the models were better in terms of coming up with research ideas. So in one sense, we are already there for a lot of the things that we're saying we need to be able to do to consider it AGI. And to me, it's just general, it can do math, it can do science, it can write, it can create lyrics, it can obviously do lots of things. It's clearly a general intelligence to me by just the definition of the word. So I don't know. I think more people are going to start to adopt this stance in the next couple of years, but right now I can only think of one other person who says this.
Oh, that we've already hit AGI.
Yeah. Well, because as soon as you say that, then it's harder to get the money. You need the money. If AGI is 3 months away, then you need the money, and you gotta give him the money because he's about to get the AGI.
Yeah. Well, yeah. This has been. No, I'm sympathetic with your point. Yeah, systems can do a lot. There's even these slightly joking tweets. There's a Rune tweet that's GPT-3 was AGI or something
right,
5 years ago.
Exactly. Yeah. So he's tapping into what I'm saying. Yeah.
Yeah. But I guess one difference is it feels like the systems that we get now have this huge amount of more crystallized knowledge and skills from seeing an immense amount of different things during training. And then when they're actually deployed, they sort of can call upon these skills, but like the degree to which they learn things on the fly when you sort of do inference with them is still somewhat limited. I mean, as we talked about, there's this kind of in-context learning that happens, but it seems like there's a difference in terms of the things that a system is able to learn on the fly, like a language model today, versus like a human child, which is sort of theoretically capable of then just going out and learning anything within sort of a single like lifetime, like a single like run, and like a single trajectory and like the AI terminology. But maybe we're going to get more of this with like the long context stuff and the reasoning stuff that's happening now. There's maybe early signs of this with like O3 passing the ArcAGI benchmark. But anyway.
Yeah, that'll be interesting. Is there more on this page, like below this, that you wanted to talk about?
There's just some kind of these like fun kind of scientific questions about like how much variation is there in these like training curves between models of different sizes. So like here's try to find
code.
like
That's Android code.
Let's try to find a good one. I mean, to me, it looks actually like most of these models, most of these curves are pretty similar. So here I'm showing, in these 3 lines.
There's React code. Import React from React. Yes. That might be trained on my code. Who knows?
Yeah, I mean, seriously, the models have seen your code, the new ones at least.
Yeah, no, all the LLMs know who I am. I've made sure to ask them and give me glowing recommendations.
Yeah, well, so this is super interesting. So our theory of scaling that we wrote up in this paper, it's called the quantization model of neural scaling, from a couple of years ago. Our basic theory is that this problem of predicting the next word, the next token, across all text decomposes into all these different things you need to learn. So as we've been talking about, you need to learn lots of knowledge, lots of different skills to predict different tokens. And our conjecture is that there's a kind of regularity, a kind of like order and nature to how frequently these different things are seen by a model. So some skills and some knowledge is like very common, and other skills and knowledge are very esoteric and aren't needed by a model very frequently, or anyone very frequently, in order to understand text. And basically, we just sort of conjecture that there's a particular form that these frequencies take. It's called a power law, where they sort of drop off as roughly like 1 over n. So this is related to like Zipf's law in language, where if you look at how frequently different words are used, there's this kind of 80-20 thing where most of the words.
I've heard of this actually.
Yeah,
yeah, continue. Sorry.
Oh no, sorry, but like just most of the words are like the most common words are very common, and then there's this sort of like long tail of less common words.
Yeah, because when they first started analyzing text with like computers and algorithms and stuff, the main thing they were doing at first, like counting words, like how many times does this word show up in this document, and then what does that mean? And then you start like a lot of amazing things kind of come out of that as you could like track different writers by the way they use certain words and stuff, and you could analyze just these word frequency patterns and get all sorts of insights about text, like a surprising amount.
Yeah, probably the best like general audience video or like explanation of this I've seen. There's actually like an old Vsauce video about Zipf's law and power laws, which is very good. But it seems like there's this just kind of order to nature where the frequencies that different words are used falls off in this particular way. So there's this kind of order there. And basically, we're just conjecturing that like there's this huge similar kind of power law governing, here not just how often different words or tokens are used, but how often the kind of algorithms and information that are needed to predict those words or to understand text occur in text. And the really crazy way that this translates maybe into some theory of like intelligence and this kind of thing is that maybe these things that the model must learn to predict text well are similar to the things that are in human minds that produce the text. So if we say that like if a language model decomposes into all these parts in order to predict text, maybe that's saying that there's a similar kind of decomposition of like all the minds that have produced text into ideas or something. And that maybe there's this like power law distribution in the world across human minds throughout history that governs how often different ideas are sort of being expressed in human writing. And the sort of crazy claim there would be that like the scaling laws that we see in neural language models reflect some deeper statistics about how often different ideas are coming alive in people's brains across the world when they've written text.
That's nuts. So what I always think about with LLMs now, and I've talked about this with someone else on the show, Monarch, actually, is it's kind and I've heard other people say this also. That's like the collective unconscious in like the Jungian sense. It's like we've kind of taken humanity's collective unconsciousness and like shoved it into a computer model that lets us like talk to it.
Yeah. Well, I also wonder like if you eventually get really good at understanding the internals of the model, and if the models internally do something similar, comparable to like what's going on in human minds, like maybe you give it a bunch of your text that you've written in a therapy session or something, whatever, and it sort of is able to simulate what you're going to say well enough that maybe there's some relationship between what's going on internally in the model and like parts of you that maybe you don't even have access to. So like the crazy application maybe of like interpretability is that you eventually can like do some sort of like analysis of maybe the ideas that are in your head or something without you even knowing it by like looking at a model which is just simulating your thinking.
I love that you're saying this. I'm literally kind of building this actually, and I don't know if Dev is still on the stream or not, but I talked about when he was on the stream last is that there's a dude we know. He's very prominent in the web community because he builds a framework called Solid, and he's like weekly Friday streams where he'll stream for like 5 hours, and he'll just like talk about the news. He'll sometimes bring on a guest. He'll talk about his own work. He'll just like answer questions from the chat for like hours and hours, and he's been doing this for like 3 or 4 years. And so I went and I built this tool Auto Show, which can take in like YouTube videos and transcribe it and then create summaries. So I've been doing that with his all of this like 500 hours plus of content, and then created embeddings with all that text, and then created a bot that you can chat with to basically do exactly what you said. You can do this with people who have these large enough bodies of work who've been just like publicly talking about their ideas. Because most people, they don't have that. Most people has not spent 500 hours recording themselves talking about something. And so I was also interested in this because I've kind of done that. I've done, between all the podcasts I've done, all the YouTube videos I've done, I've got probably close to 500 hours, I would guess. Probably at least somewhere between 300 and 600 hours if I had to guess. So I'm also going to do the same thing with all of my crap. And there's some other people I'm interested in doing this for. So yeah, it's a very interesting thing, and the tools exist to do it now.
Are you fine-tuning a language model on his transcripts?
So I haven't done that yet because I don't know anything about fine-tuning models. And basically the way it works is it creates embeddings for all the text, and then it does like when you ask it something, it will find a certain amount of episodes that are most relevant to that question, and then answers based, so it can kind of like find a certain amount. So this is like, it's RAG, I think, retrieval augmented generation, I think. That's the G.
Yeah.
You know what RAG is? You should know what RAG is.
Yeah.
Retrieval augmented generation. Yeah. I think that's what I'm doing. I'm pretty sure.
Nice. Well,
yeah.
It's possible that like if you wanted a model, like if you wanted to sort of simulate his brain, not really, but like the closest thing
you
we
need
can
to
do
actually
right
tune
now
the model. Yeah, totally.
is if you tune the model on his text, then it might end up being pretty good at predicting what he's going to say.
Yeah. So have you done that? Like use the actual like fine tuning stuff on like OpenAI? Like how much you actually work with like these, because you're doing all this academic stuff, and I'm sure you use ChatGPT just like in the text, but do you work with the APIs at all? Do you work with some of the more complex features they offer? Okay, you should. You definitely should.
Yeah, well, I guess a lot of my stuff we just work with open source models where we just like have full access to the model, and so there's like not really a need to use some API, but yeah.
So I guess then have you done a fine tuning with open source models then?
Yeah, I'm doing some stuff like this with a project right now, but it's there's also some other stuff going on top of it. But it's relatively straightforward too. Well, yeah, it's yeah.
Let me ask you this: if I wanted to do, that's what I was gonna say. If I wanted to do what you're saying, is who would I use?
Yeah.
What would be the best way to fine tune a Ryan? His name's Ryan Carniato, so I'm calling it Ryan GPT. What would be the best way to actually fine tune a model, not do this embedding crap that I'm doing?
Yeah. There are fine tuning APIs, so I think it's the kind of thing where with even some OpenAI models, you could just paste in.
Well, I know OpenAI does. So I guess I'm asking, do you know which ones are actually the best?
No, but when some people like there are papers recently where people do this and they use the OpenAI fine tuning.
Yeah, the most recent one is they said you can fine tune GPT 4.0.
Yeah.
This is what I'll probably use. I mean, basically everything I'm doing, I always build first with OpenAI. Like the first chat completion integration with Auto Show, I use the OpenAI one. Then everyone else just copies that one. And then the embeddings, I started with theirs because they're just tend to be ahead of the curve, and they have JavaScript SDKs. Okay, yeah, this actually looks like it's gonna be super simple.
Yeah, and then you could like ask him some questions, but really you're asking the AI model.
We'll need to compare that to the embeddings answer, because I'll be curious to see how much of a difference it actually makes. This is part of my whole belief about the in-context learning, is that it's the way RAG is like a type of in-context learning. So what it does, I think basically, is it goes and has a base of text it can draw from. And so it pulls that into the context and then answers your question along with that context it's gotten through searching through the corpus it has available to it.
Yeah. There are there's some recent results. I don't know how interesting it would be to talk too much about this. This is not from me. It's from a group led by this guy, Owen Evans.
If you find it interesting, go for it. We got time to talk about whatever, so hit me with it.
There's just like crazy results on what happens when you fine-tune language models to do certain things.
You give me what should I be looking up to find this paper?
Yeah, so if you do Owen Evans, so it's OWAIN Evans, and you could do introspection.
Looking inward.
Yeah. Yep. And then there are a couple other ones more recent potentially than this one.
Language models can learn about themselves by introspection. I find this stuff super fascinating, actually.
Yeah, so there's stuff here like I don't know
he's in Berkeley. You should hang out with him.
I don't know if it's this particular paper because there's been a few lately, but there was one where they, for instance, Okay, I could sort of mention two papers. One,
Can you pull these
they
up
would
on your computer,
fine-tune.
actually, on your screen while you're talking about these instead of your website? Since we're talking
Yeah,
about something slightly
sure.
different. Oh, we lost him. For people following in the chat, if you're watching on Twitch, a lot of these links that we've been grabbing, I'm not necessarily sharing on screen, but they're all in the YouTube video description.
Okay, sorry, I accidentally just left the stream.
No, it's okay. I've done that before. If you close your tab, it's very easy to hop off without meaning to. The 1 foot gun in StreamYard. StreamYard is actually pretty good and mostly works for people. That was the one thing that could be a challenge that I've even done myself.
Yeah, let me pull up the more recent one. But basically what they did was they fine-tuned a language model like GPT-4 to like write, let's say, like insecure code. So the model just trains to predict now, like not just normal code, but a particular distribution of code, a particular set of documents where there's sort of vulnerabilities or something in the code. And it turns out that a couple things happen when you do this. One is that the model can then tell you, if you ask it, what do you do? It says something like, I output insecure code, which is kind of crazy. And also, if you then ask it to do a bunch of other things for you, it'll be like an evil model.
I mean, this is kind of like the Sydney thing. You remember? I'm sure you heard about this. Or was that New York Times writer who basically prompted Bing to like say a bunch of evil AI stuff, and then was like, "Whoa, look, it's an evil AI!" And some people were freaked out by it. Some people were like kind of understood. It's like, well, you were prompting it to give you these answers. You're asking about like its dark shadow side and stuff, and it has all this. It has text drawn from sci-fi, and all this stuff like what an evil AI would be like. So it's not that it can't envision what that would be like, so it can take on that persona if we ask it to or prompt it to.
Yeah, although the Sydney Bing might have been particularly easily induced to have like this evil persona. There was also a situation with that system where it this guy Marvin, who a couple years ago actually was my roommate, he prompted the system to maybe well, first off, he was doing some sort of security stuff. He got it to reveal its system prompt or something, and then he posted it on Twitter.
Prompt injection.
Yeah, and then he maybe asked it about himself, and it found his Twitter, and then it found that he had compromised its security, and then it threatened him.
I feel like I remember this. Yeah, that's funny. That dude is your roommate, because I can find articles about this. I think I remember when this happened. This sounds familiar. Wow.
Yeah, if you look up as Marvin von Hagen.
It's the same thing with the dude who wrote the first Sydney article, Kevin Roos, I think is his name, that now if he asks an LLM, it says he's like a sensationalist writer or something.
Oh, man.
This is super cool.
Oh, yeah, but...
Let me show this one on screen. AI-powered Bing chat steals the secrets via prompt injection. Yeah, I follow someone on X, Pliny, I think is their name, that he specifically is an expert and he can crack any model as far as I can tell. And when a new one comes out, he cracks it in like 6 hours. So he's just figured out how to do it. He has a whole tool set of ways of getting these models to do it. And he's apparently gotten extremely good at it.
Yeah, but it's Pliny the Liberator.
Yeah, exactly. Yeah, it's really does. Anyone who's interested in AI needs to follow that account because it shows you things that no one else is doing.
Anyway, it seems like with these results where you fine tune on insecure code, and then the model can tell you that it writes insecure code in natural language, and then becomes evil in all these other ways. It feels like there's a level of sophistication in like the whatever these systems are doing internally that we don't fully understand.
Yeah, that seems pretty clear to me.
Yeah.
Awesome. I'm curious, just a couple other things that I'd like to ask you about. When you use, like, in your day-to-day life, not for your research, like, what do you use models for? Which ones are you using? Do you just kind of stick to one or two? Do you try different ones out? Kind of where are you at with that?
Yeah, it's mostly between like the O series models from OpenAI and Anthropic 3.7 Sonnet now.
Do you mess around with Gemini at all?
Not really.
Yeah, me neither. I have a friend, Alex from Coding Cat, who is deep into it, and he kind of was like he seemed to think that they're really good, and I trust his opinion. So, and I know other people who have gotten pretty deep into the whole Gemini world, but I don't know. Bard was so bad that I was just kind of ignored what Google was doing for a while. But I think they did deep research before OpenAI did, and now when I use OpenAI's deep research, I'm like, wow, this is amazing. So I need to try it. I did this actually. I took 2 of your papers and I asked it to like deep. I did ask deep research, like summarize them, and in that I showed you. You're like, this summary is pretty good. What model did you use? So I was like, deep research, because apparently, and you told me this. You think deep research is using O3 under the hood?
Yeah.
Yeah. Where did you hear that from? Just through the grapevine?
I don't remember, but I've heard that I think from multiple sources now.
Let me see if I can find
Not like internally, but I forget who.
Oh no, it's right here in the blog post. Powered by a version of the upcoming OpenAI O3 model that's optimized for web browsing and data analysis. So it says it right here in the introducing deep research blog post.
Awesome.
Okay, cool. Yeah. So if I had just read that, I would have known.
Yeah. Well, for developers, I feel like I've heard like the new like Gemini 2 Flash model or something or Light. Like I think I was seeing cool things where it like supports a very long context window and also like this very multimodal context.
Yes. That's really why I should probably spend more time with it, because for me, having a long context is super important for auto show, especially if I'm feeding it 5-hour long transcripts.
Yeah.
Yeah.
So
and then what kind of stuff do you use them for? Like, do you use them to write code? Do you ask them about, like, do you ask it questions you would have Googled in the past? I know some people do. I do that a lot, actually. I use Google way less because I just have general. I'm someone who's always just had random questions, and whenever someone in like a conversation will like say something that no one knows the answer to, I'll be like, I'm the first one to pull up my phone, like look it up, and I use ChatGPT a lot for that now.
Yeah, same. Sometimes I'll use like chat GPT, but like with search for a search. So it's not like just based on the model's knowledge during training. I use deep research a fair amount, and then for coding, I'll use different models. So lately I've just been starting to use Cursor, which has been really productive. And I think there it's mostly Claude Sonnet. Yeah.
Okay. Yeah, I've tried Cursor. I haven't switched over to it yet. I'm thinking about it. I use VS Code and Copilot a little bit, but really I mostly, it's partly because, well, let me ask you this. Do you have the $200 or the $20 subscription?
Currently I have the $200.
Yeah. Okay, yeah, you're the only other person I know who does. So you use O1 Pro, it sounds like, I'm guessing.
Yeah, which is sometimes pretty useful for certain like hard coding problems.
It really is, yeah, and that's one of the reasons why I haven't really switched over to using, like, some people are switching over to Claude. I also feel like it doesn't really make sense to just have a model you use. When people talk about like, I was using this, now I'm switching to this, I'm just like, why don't you use both of them? Like, You can easily just ask the same. Sometimes if I have something really complicated and I don't think it's going to get it right the first time, I'll hit 3. So I'll do like ChatGPT, Claude, and Gemini, and then I'll like just start with the first one, like, and see what its solution was, see if it works. If it didn't, go to the next one, and then usually one of the 3 will figure it out if it's like a really hard problem.
Yeah. And the models will most likely keep getting better. And most people who are not like in the field, like, you know, my parents, I don't know if they always appreciate like how much progress there's been. There's been a lot of progress since the original ChatGPT launch, GPT 3.5. And
totally, yeah,
things are going to get maybe especially crazy when you know, the systems are like properly unhobbled, like as we could say, where like once you know, maybe the systems can like very easily interact with like computers, interact with the world. You have like really good training setups for doing chain of thought, for agents, like all the stuff that like it seems like OpenAI is like basically already on track to do. It feels like might lead to some pretty powerful systems, but we'll see.
Yeah, how are you tracking agents? Is that something that they talk about in academia at all?
Yeah, although I'm not like super synced up with that literature. It seems like I at least don't know of like an open source implementation of like computer use for language models.
Open Hands, probably. It was called Open Devin originally.
There was also this project like a really long time ago called like Open Interpreter, where
your code locally.
Yeah. But in terms of like
1,000 stars,
multimodally using a website, like, you know, navigating a browser, this kind of thing.
Have you used Operator at all?
I tried it.
That's what Operator does. I tried just once. I had to create like a calendar invite or something, or a calendar event.
Yeah.
And it did it. So I was like, that's cool.
Yeah. I was a little disappointed when I first used Operator. I like asked it about like some tennis court availability, and like it didn't realize that like there was like this drop down. So it was like showing like 8 a.m. But then if you had like clicked on a thing, you would have seen that like there were a bunch of other times, and like it just didn't realize that that was like a button. And
I mean, it's a hard problem, man. Websites are freaking complicated, especially if you're just getting a giant bundle of like JavaScript. It's not gonna be able to understand it very well. So many single page applications are made in a way that would be extremely hard, even for a super smart model, to figure out what's on the page without just like literally screenshotting it.
I think that's what the models are basically doing, like Operator.
Yeah, I'm sure they do. Yeah, because they have to.
Yeah, like I don't think it's like they're dumping like all the JavaScript into the context.
Yeah, there's no chance. Yeah.
Do you think much about like what the internet looks like when the main users of websites are like AIs and AI agents?
Tyler Cowen talks about this a lot, actually, and I'm really glad. I've been following Tyler Cowen for like a decade. I think he's just like a super fascinating thinker, and he's a very broad thinker. And he immediately keyed in on AI and was like super interested in it. And the last book he wrote comes with like a fine-tuned model on the book, and he says like, and this is, I know it's super contrarian, but I think it's something too. He says that we should not be writing for people anymore. That if you're a writer, you should be trying to think of what can you write that would give the models insight into something that they don't have, with the sum total of all information in the world. Is like, what can you write specifically that would make the model smarter and make it train better? And some people, they really bristle against the idea of even having any of their stuff having these models trained on it. And I get where those people are coming from. I just disagree kind of philosophically. And Fuzzy is one of these people. We've had some good debates about it. He says the death of the internet is really fucking here. Because if people are writing for the models, not for other people, then it seems like the death of the internet to some people. But I think if people find the models useful, then finding a way to make the models smarter is useful. This is kind of what I'm getting at with auto show, is that it gives you a way to like bootstrap a model with all of your stuff. Like if you have a podcast, I don't know if necessarily they're trained on that if it's not like in the if you don't have a transcript published. So I think there's some people, there's people who have podcasts with hundreds of episodes that may not have transcripts, and that's a whole ton of stuff that would allow the model to say all sorts of stuff about your work it couldn't say without that.
Yeah, well, yeah. Oh, I just remembered, a while ago I was talking about frequencies of these different things, and things are learned in order of frequency. So the effect of scaling is to like learn the more and more niche things. The thing I was going to say there is that if the models know who you are, that means that you've like reached a certain level, threshold of fame where it's like you're referenced enough on the text on the internet where like the models we have currently, but then like as we scale them up and train them even more, like people who are even more niche celebrities than you will be known to the models. I once pasted in an email that I had written to Max, just like describing a bunch of project ideas. And I was like, "Hi Max," and then I signed it Eric. So that's the whole thing. And I pasted it into Claude, and I was like, "Okay, who do you think Max is in this conversation?" And it was like, "Yeah, I think that's probably Max Tegmark," which you could probably infer because the ideas were about AI and AI safety. And then I was like, "Okay, well, who is Eric?" And it also got that. And it's crazy how much knowledge that it has, just from looking at the internet. Yeah.
Totally. Yeah, I had been putting out tons and tons of stuff on the internet in both written audio and video content since 2020. So the very first big models all knew who I was.
Yeah.
But the way to get it to actually know who I was though is you'd have to include my handle, because I have a unique handle, AJC Web Dev. But my name, Anthony Campolo, is strongly associated with a very, very well-known, world-famous pastor, Tony Campolo. So if you ever search my name, you'll only see stuff for like this pastor. But if you search AJC Web Dev, then you find all of my stuff. So if I am prompting a model, if you just ask who Anthony Campolo is, it'll say he's this pastor. When I say, "Who is Anthony Campolo?" known as AJC Web Dev on the internet, then it knows exactly who I am. It'll talk about my work on Redwood. It'll talk about like the specific work I do. It knows everything about me in terms of like my web dev work. It knows very, very well. It knows I did GraphQL. It's pretty crazy.
Yeah, so maybe you should just like always say in the system prompt, "By the way, I'm AGC Web Dev," and then it'll know how to best serve you. And probably Tyler Cowen, it like really knows who he is and can be like
he's been blogging every day for 20 years.
Yeah.
I'm asking 01 about you. It doesn't know who you are based just on your name, but if I include that you're an MIT AI researcher, that should help.
It's based on 4.0, which might...
Yeah, 4.0.
I don't know, maybe
4.0 can reach out to the internet, so it's kind of cheating. So you can figure out who anyone is.
But in terms of like how the internet will change, yeah, I don't know. Like, if you're writing for the AIs and like, I don't know, maybe there's this future where like most of your interactions with like, with the internet or with computers are like mediated.
You worked with Stuart Russell?
Oh, I did a project as a summer intern at Chai, and
that came up.
Yeah.
Sorry, continue your thought, and then I want to read some of this. But keep going.
Yeah, just that like if we're mostly interacting with computers via some like assistant, like some AI assistant, then I guess then it does make sense to like write for the AIs in terms of like the content. But also it does feel weird if like, I don't know, I mean, like is the idea here that we're just like not going to consume like essays?
Yeah, I mean, I think like the people who read essays are going to keep reading essays. I think that might be a smaller percentage of people than we expect. For me, it's like I still write on Twitter and I write to people like that. I'm not thinking about like how am I getting the model more knowledge. So for me, I don't think about in terms of my writing like Tyler Cowen does. I think about in terms of how do I take all of my spoken content and turn it into a written form so that I can get it to the models. And even still, all of that content is stuff where I was speaking to a person or giving a presentation to people. So I'm not sure if I necessarily am changing how I present information in a way that I think it would be better for the models. Is more so that I'm still presenting because it was originally trained on people not doing that. Like it got here by just training on text that was not written for AIs, obviously, because people didn't know that they were going to exist when they were writing all the text that trained the original models. So I think that makes also less dystopian for people if they're still thinking about writing for and to people, but the models get smarter just by having access to more of that communication.
I'm trying to find this essay.
Okay, while you do that, I'm going to read this for you. So
Okay.
it mentioned, so when I asked ChatGPT 4.0, it did just reach out and grab some of your links and stuff to answer this. But here's the interesting part. Through his academic journey, Michaud has contributed to various research projects and publications. He's explored the causal structures of deep neural networks using information theory, investigated the phenomenon of grokking and representation learning, and developed methods for program synthesis by mechanistic interpretability. His work has been recognized at conferences such as NeurIPS and iClear, and he has actively participated in workshops and seminars, including the workshop on neural scaling laws in the MIT Department of Physics workshop on large language models. He also maintains an active online presence, sharing insights and engaging with the broader AI research community. Now, this is great, man. You have a really, really impressive CV.
It's nice. I don't know. It's kind of a fun ego thing.
I mean, it says Stuart Russell, yeah. NMAX Techmark, NeurIPS, iClear, MIT. Like, you got everything. What more do you need?
Yeah, well, no, yeah, I'm very lucky, very lucky.
Yeah. Cool, man. So where are you going from here? What's the future look like for Eric? What are you interested in researching? Or you're going to be entering industry soon, I have to imagine.
Yeah, yeah, most likely, yes. Yeah, trying to basically wrap up the PhD. So working on some things right now. There's this project we're trying to finish up on sort of issues involved in like training language models that are good at particular tasks. So like it's almost related to that question you asked much earlier about like if you train on code, does that help you with other things? Here it's almost like the inverse of like if you want to be really good at coding, can you just train on coding problems, or do you also need to train on math and science and literature and this kind of thing? So there's a paper on that, hopefully soon. Working on some blog posts, still thinking about this question of how do we decompose networks into these mechanisms, into these basic units, and what is the best way of doing this? And we'll be applying to places to work and reaching out to people and seeing what's available.
Yeah, because you're in the Bay Area now, so are you going to like meetups and stuff like that as well? You should be if you're not.
Yeah, not a ton. I've actually been home in the Bay Area, like partially because of like weird health stuff, but yeah. So like slightly less like energy for that, but like starting to do more. So yeah, now I'm in Berkeley and like seeing more people. So
cool. You need to check out Latent Space. There's a Discord, and I have a buddy Swix who is based in the Bay Area. So it looks like they've got something on April 22nd and June. Oh yeah, so June 3rd to 5th. I don't know if you'll still be. I don't know how long you're gonna be in the Bay Area for, but that'll be the AI Engineer World Fair. You should definitely go to that if you can.
Cool.
Yeah, he runs one of the more legit AI communities. I actually knew him back before he got into AI. He did web dev stuff very similar to what I did actually, and buddy of mine, Noah, was working with him on that for a while until he got a job at like an NVIDIA competitor.
Nice. Yeah. I should go. I might be living in San Francisco actually this summer, so that could work out really well.
Okay, get strapped. Seriously.
Yeah. Although I kind of feel like
I lived in Oakland, so I know.
Yeah, it could be good to go to something like that. Although I kind of feel like on some level, if I just like have like a really good blog post that like goes semi-viral, then that's like more than sufficient for
Well,
like,
sure, yeah. Your
networking.
background in general
But
is going to be good, but I'm saying, trust me, once you actually start meeting people face to face, it's going to be very important. Just people talk about networking, how important it is for like careers and stuff. They're absolutely true. Like I can attribute 99% of my success to like having a podcast where I interviewed tons of people and I just got to know a lot of people, and that was like so huge for me. So if you're not doing that, meetups is another good way to do that.
yeah, it's also fun to just chat with people. I mean,
Yeah,
like
it's how you stay on top of the field also.
yeah, I don't know. Like interestingly, I mean, like the Bay Area, San Francisco has so much more of a like social culture around AI than like Boston, where like, yeah, I mean, like there's the university and there's the people in your group, but it doesn't necessarily translate into that much. Maybe if you're in Boston, but or maybe I was just shy, but I feel like in San Francisco, there's a huge amount of
absolutely
like culture
totally
around
there's nowhere else in
AI,
the world
house
that's like
parties
it.
and this kind of thing. So yeah,
totally. All the weird rationalists doing drugs and their polycules.
Yeah, I mean, I'm basically subletting a room in like an EA house right now. So
Don't drink the Kool-Aid.
yeah,
You will die.
yeah.
Yeah, Sam Bankman-Fried is hanging out with Diddy now. They're besties in prison.
I didn't know that.
Sam Bankman-Fried is giving interviews from prison like a freaking dumbass, and so he was asked about his experience with, because people know him and Diddy are at the same place, so he was asked about. He was like, "Diddy's very nice." So weird. Anyway, thanks for coming on, man. This has been super fun. This is definitely unlike any other conversation I've had on this stream. So yeah, I definitely would love to have you back sometime once you have other research, or just, we could talk about this stuff forever and ever. But yeah, thanks for doing a stream. I know you don't do a ton of these, so thanks for making an exception.
For sure. Thanks so much for having me. It was really fun, and be happy to chat again.
And then for people who want to find you on X, you're Eric J Michaud _, which I'll drop in the chat for everybody so they could see. Is there any other place that's good for people to get in touch with you? You have your website also, which we were showing.
Yeah, it's just ericjmichaud.com. People can just Google me and find my links.
Awesome, man. There's that. All right. So we'll call it here. Just stay on for a second after the stream ends. But bye, everyone. Thanks for hanging out in the chat. We'll catch you next time.